All right, I guess I can start. Thanks for the invitation. It's really nice to be here, and it's nice that I was part of the RQI circuit last time here as well, and I agree that the room is much fuller now, which is nice. Anyway, so today I want to talk about the notion of subsystem independence in perturbative quantum gravity. A lot of this work is based on a review that's being written within the context of this collaboration called eMERGE, and mostly Jan, Glowacki, and I are leading the effort. Okay, so let's start some motivation. We like to think that there should be a notion of background independence in our fundamental theories. There is also some notion of principle, kind of like principle of relationality. I'm not calling relativity because I don't want you to think about space-time only. So things should be somehow relational. We like to think like that. And because of that, we learned that there is some sort of like breakdown space-time in time and space is not particularly absolute. And in fact, it's dynamical as well. Now, there is a nice paper by Zurich from 2007 that he postulates the zeroth axiom of quantum mechanics that usually don't read quantum mechanics textbooks, which is the world consists of systems. And so then you can start thinking like, well, are systems absolute in a way that challenge background independence and this idea of relationality? Or rather, the way that you think about quantum systems in the context of like Hilbert space assigned to them, maybe is also something that shouldn't be absolute, but should be somehow relational, maybe even dynamical. And moreover, my own research, which is a lot in space-time emergence, if I want to think that space-time emergence, or maybe space, not so sure about time, is emergent, and we infer space and time from physical systems, and we know that space-time has all those nice things about being relational, perhaps there is something about the way that you should understand systems in a different way that we do nowadays. Okay, so the take-home message is going to be very simple. It's going to be this, that when we start in thinking of not having gravity and just normal book quantum mechanics, everything goes really well. And as we push things towards quantum gravity, we have a lot of questions that remain unanswered. And hopefully by the end of the talk, you're going to appreciate a bit more about the kind of problems that we face. Okay, so let's start with no gravity. By the way, my slides are going to have math and stuff. You can always come back to them. But I'm going to keep more narrative. And if you have questions at the end, we can actually come back and look more closely to the notation and to the mathematics. So what's a quantum system? Typically, we think about quantum systems by having some kind of Hilbert space. There is typically some state space, some convex set. We're going to be thinking about density matrices here. And there is also some space of observables. And typically, by having this triple, we characterize, at least kinematically, what we mean by a quantum system in quantum mechanics. So naturally, you can ask, what is a subsystem in quantum mechanics? And a subsystem is going to be just like a system, but now you have to somehow be able to talk about that in the context of an enlarged system. And typically, one way to do that is to think that you can have your subsystem, its algebra observables, for instance, embedded into this enlarged quantum system. And you can define those embedding maps where you take observables from your local subalgebra and now embed as a global observable. And you can do something just like that, basically taking the dual of that and define also restricted or density matrices. In the case where you do have a factorization of Hilbert space, that's what we call a reduced density matrix. And typically we define them by just impose the expectation value as seen from the subsystem point of view can be now written in terms of the quantities defined over the global Hilbert space. And again, as I said, typically those maps, they become just tracing things out in typical quantum mechanics. Naturally, the question is, okay, so I told you what a subsystem is. How do you know you have more than one subsystem? And then we get into the notion of independence. How can we talk meaningfully about having different subsystems? And it turns out, as you can see here, things start to become more interesting. There are different notions of independence that we rely on when we do quantum mechanics, quantum field theory, quantum gravity, and they are more or less connected. And I will try to convince you that when you do quantum mechanics, textbook quantum mechanics, they all collapsed into this single structure that we call the tensor product structure. But you can disentangle all those things, and we better do, because we're going to go to more complicated regimes where those things don't become that equivalent anymore. So let's start. Just let me say that also everything that's in black here are things that you can think more operational, while the things that are in white, like what's a tensor product structure, is something very abstract and algebraic. But the things which are here in black are things that you can think as if you go to your lab and you have your notebook, your data, and you want that notebook to have some properties when you gather data. And those things here, they encapsulate that. I'll explain why. So the first one, let's focus on statistical independence, which is also sometimes known as state preparation independence. The idea that you can go to the lab, and if I have system A and system B, I can prepare their states independently. And so statistical independence means that if you have two subsystems, they will be statistically independent. If for any states on each of those subsystems, you can find a global extension that when you restrict this global extension to each subsystem, you recover the state that you want to have prepared for each of them independently. So we can write everything in a more succinct way, and you can come back to that later if you want to understand the notation a bit better. But basically, the idea is that we demand compatibility of the marginals. When you take the marginal probability distribution, they should match up if you start with this global extension. Naturally, you can think about failure. When does that fail? You could have thought that you have a system like a cube, and somehow you thought that the different corners of the cube were independent subsystems. And then you want to prepare this corner to be up and this corner to be down. Then you find out that you cannot. And you cannot because there is a constraint. So whatever states that they have that you're going to prepare those corners is going to depend on this enlarged system, the cube or the die that you throw. And therefore, you do not have, for every possible state that you want to prepare for those, a global extension. And here, just to give you already the intuition that in the presence of a constraints, this kind of a notion suddenly becomes non-trivial. You can ask even more. Not only you can think about statistical independence, you can think about statistical independence in this product sense. And this is just a fancy way of saying that not only you want this global extension to exist, but it should exist in a way that is a product state. So basically, you can just write down the definitions. This is inspired on the idea of independence of events. When you just think about pure probabilistic theories, that you have, if you have two events that are independent, the joint probability factorizes as a product. And you can demand that also for your global quantum state, your global extension. That for every possible states in each subsystem, there is a global state such that its joint probability distribution over the observables of each subsystem factorizes as a product. And naturally, it is a stronger notion than the previous one. And so if you do have this notion, you imply that you do have statistical independence. So I've been focusing a lot on the existence of states. This was the lower part of this diagram. We can now look to observables. And we have two different notions. One is joint measurability. And so joint measurability means that if I have two pairs of observables for each subsystem, then there exists another observable defined on the global Hilbert space, such that you can use that global observable to derive or recover what would be the statistics associated to each of those observables. And here, of course, is just, again, just notation and math, how to define those things precisely. But what I want to tell you is that you can show that if you impose joint measurability, that implies that those algebras, they have to commute. And you could also have thought about that in a simplified way, just by thinking that if you think about this as observable to self-adjoint, and this is self-adjoint, the product is not self-adjoint unless they commute. That's a quick way to think about why this should be true. You can also think about non-disturbance. What does it mean to make a measurement on one system that does not disturb the other system? And of course, in the literature, this is more usually thought about in the context of non-signaling, but we don't need still to embed any of these in space-time. And so the idea is that if you make a measurement on one system and you do a non-selective state update of the state, of the global state based on that measurement, then just can apply. So this is the general state update. You can apply now for one of the systems. And then you demand that the statistics of every single observable of the other system remains the same if you consider the original state or the updated state. And of course, this just means that you can show actually that if you impose that for every single element of, or every pair between the two algebras, that also implies that the algebras commute. So here we talked a lot about expectation values or data that you can gather. That's why we're covering all of those. But we already saw that we have this commutativity appearing here, which can be typically is called observable independence. So just to flash the slide, we can take the embeddings of those algebras into the large Hilbert space, and we say that there is a notion of observable independence if the subalgebras commute. So all of that is probably quite familiar to all of you. And the key point of this diagram is to say that all those different notions, they can be in the context of having finite-dimensional quantum systems. You can show that by just imposing that you have a tensor product structure, everything follows. And that's why maybe we don't think too much about that when you're doing quantum mechanics. Now, just to recap, in case you don't know, when we mean by tensor product structure, basically this idea that you can factorize your Hilbert space in different factors, and then there is a formal definition of how this factorization works, because it's not just a unitary that takes this Hilbert space into this isomorphic Hilbert space, but actually is a unitary modulo, the fact that you can rewrite this unitary or those factors as with local unitaries. So really, a TPS actually defines a particular equivalence class of operations that you do or mappings that you do between this global Hilbert space and the isomorphic one. And then there's a theorem that goes back to Zanardi and others in the early 2000s, but it can go all the way back to literature in like algebraic QFT in the 60s, 70s, that if you have some interesting properties such as that you exhaust your system by doing this factorization, then you can show that it is if and only if you have a tensor product structure that your observables commute and can be embedded as von Neumann algebras on a given Hilbert space factor. Okay, so if we go back to the diagram, we can actually write down everything quite mathematically, and this is all very nice. And so just a recap, this is the central notion that we're talking about here, which is defining our quantum systems, and it's guaranteeing us that we can make measurements which are independent across those systems, and guaranteeing that we can prepare states independently across those systems. Now, of course, I just said a lot about quantum mechanics, but it turns out that by demanding those notions of independence, preparation of state, and measurements, you can actually apply this very same construction across classical mechanics, and then there you have the Cartesian product, not the tensor product. Quantum mechanics we just reviewed with the tensor product, but you can also do that in quantum field theory, and things start already becoming a bit more fuzzy. I won't go into details, we can come back to that later if you want, because there not only you have to rely on the notion of commutativity, you also have to rely on some more abstract algebraic properties, which has to do with the fact that local algebras in quantum field theory, they're what we call, they're not type 1 von Neumann algebras, they're type 3 von Neumann algebras. But we won't be covering much of that here. This is to tell you that everything that we did so far is quite well generalizable in the context of QFT as well. But I'm interested in gravity. And so if we go towards low energy, perturbative quantum gravity, things start becoming a bit complicated. All this picture that looks quite nice. So it turns out that if you think that you can model low energy quantum gravity as a quantum field theory, and you want to canonically quantize this quantum field theory, there are some results that start to prevent us from thinking about those properties that were quite nice, that allow us to connect all those things together. One realization comes from this paper by Donellis and Giddings in 2016 that basically shows that if you start with what would be space-like separated operators in your quantum field theory, if you have some scalar field and you expect them to commute, it turns out that they are not gauge invariant operators. If we have time, we're going to go back to that. And then when you make them to be gauge invariant, meaning that they're diff invariant under the diff group, linear diff group for perturbative quantum gravity, even when things are space-like separated, they no longer commute. There's another interesting result that goes back to Don Marov, 2008, sorry, and also Raju, 2021, that shows that there is something called holography of information that happens in the context of perturbative quantum gravity, and that undermines the notion of statistical independence that we had before, of you being able to prepare states independently. We were going to be now looking at those two results with a bit more detail. But just to already highlight that this result and this result, each of them are kind of undermining these different operational notions of independence. This is undermining things that having to do with our observables and commutativity. It was like the top row in our diagram before. And this undermines the notion of statistical independence, state of preparation in low energy quantum gravity, which is undermining the bottom part of the diagram. Yes, so this is what I just said. So let's quickly review how that happens. If you think about low energy quantum gravity coupled with a scalar field, you can just write down your Lagrangian. You know how the linear diffs change or transform your metric. You also know how linear diffs transform your scalar field. That's how you can see the scalar field is not gauge invariant. You can start with two space-like insertions for this scalar field, which commute, but they're not gauge invariant, as I just said, because each of them transform. And then you can try to now build an operator that's going to be gauge invariant. This is called dressing. There are different ways of doing the dressing, but all of them arrive at the fact that once you do make the dressing and make those operators gauge invariant, it turns out that the dressed version of those operators, they do not commute anymore at space-like separated regions. This is just showing how the dress operators look like. It doesn't matter so much. The crucial point is that you could ask why. I just said that in the QFT picture, everything seems to work fine. What's happening with gravity in this canonical perturbative regime that's preventing gravity from satisfying the typical dressing scheme that we also apply for Yang-Mills theories? And it turns out that if you go back to this dressing, what appears here is not only the metric, but also derivatives of the metric. And it turns out that this is typical that for any kind of dressing that we do, when you have a gauge theory, basically in the dressing, the connection appears. But what we do in normal gauge theory is not gravity, we quantize the connection. But when we quantize the perturbative quantum gravity, we quantize the metric, not the connection. So if you go back here, for normal gauge theories, we do not have this term. We only have the connection or the gauge field here. While for gravity, we have both the metric and derivatives. So you can expect that when you hit this operator with another operator, which is going to be non-localizable because they are having integrations here, at some point you're going to be hitting the metric with its derivative, and that's going to pick up a contribution that you wouldn't pick up if you're doing just normal QFT. And then there's this thing about holography of information. So there is something quite striking that whenever you have a diff variant theory, basically the Hamiltonian of the theory can be written as a sum of the constraints acting on the bulk plus some boundary term, assuming that you do have a background in which there is a boundary or an asymptotic region. It can be flat. And so that means that all the transformations, all the time evolution of all your operators, basically, if they are operators that are gauge invariant and the constraints annihilate them or commute with them, all the evolution is coming from the boundary term. And so Marov, in 2008, used this to prove something quite impressive, which is, so this is like a very quick summary of the proof. The proof, of course, has many more details, but I can give you a quick gist of what's going on here in this diagram. So the idea is to think that you have your gravity theory, and you are in past nu infinity, and you have all the different possible modes that you can send off from past nu infinity. They can bounce here and go back all the way to future nu infinity. You see that I omitted the future region here because actually Marov, in his paper, he's thinking about a black hole background. So there's a black hole here, and a lot of those modes are just going to go inside the black hole. And the question is, where's the information? Of course, it's motivated by the information paradox. So what happens here is that because you have this boundary Hamiltonian, basically what you can do is you can take any point of past to infinity, any radiative mode here, and you can translate them up and down. And in particular, you can translate all the way down here, in which you're far from this future region omitted, and you can think that you're in a flat regime here. So you translate them back, and then you evolve with equations of motion to a point in future no infinity. And if you push the limit in which you translate everything back all the way to the asymptote past infinity, basically you collapse all the radiative information that you have here around a small little region at spatial infinity. And this is what's called holograph of information. That actually you don't need to have access to every single point here or radiative mode going off, because they are all related by this translation being implemented by the Hamiltonian. And then you can actually encode all the algebraic information that would be present in the bulk in a small little region around spatial infinity. So I'm running out of time. Let me just say that if you do have, not so surprisingly, if you do have now basically a representative of the algebra of the bulk at the boundary, you can use that boundary algebra to fix your state completely. And if you do that, then basically you say that, oh, this is just saying what I just said, that you have this holographic information, that you can use the boundary algebra to fix your state of your whole quantum system. And maybe that shouldn't be surprising to you that this would lead to a failure of statistical independence, because you could think that you had a chance of fixing your quantum state inside a region with different possible configurations, while you have a given fixed state outside a particular region. But by using the holograph of information, basically you can show that if you do that, you arrive at a contradiction. And your state, as soon as you fix a state at an outside boundary region, you can fix the state inside as well, which is basically what we didn't want to have if we demand a state preparation independence that we started with before. I'm running out of time. Just want to say that there is a sense in which this picture that we had before is lost. And the question is like, what would be the lesson and how to augment this or implement this in a better fashion. And maybe for you, maybe you've never seen this before, the question should be like, why should you care? I mean, I care, I've been doing that, and I like those things, but why should you care? And is there a sense in which we should care, given the kind of physics that we do? So let me give you 2 reasons why you should care. Not sure if anyone here does cosmology, but I'm sure everyone is familiar with this. And we look to the cosmic microwave background, and we are looking to infer from these statistics different properties of what happened in the early universe. And it turns out that if you go and we study cosmological perturbations, we are modeling this using low energy perturbative quantum gravity. And typically what we do, we say that we look to different points of the sky, and we say, they of course are statistically independent. They were prepared in a state that they were independent, and we run the statistics and we model the theory, and therefore we ask for something like inflation to explain why they are so correlated. And similarly for when we make measurements across the sky. The second thing that you might make you care about this is the fact that nowadays we are also trying to probe in tabletop experiments low energy quantum gravity. And once again, we are using low energy perturbative quantum gravity to model those experiments. And hopefully everything that I told you so far should tell you that this picture where we just write tensor factors when gravity is involved shouldn't be quite there. But of course, if you open at least the original papers on gravitationally induced entanglement experiments, there are tensor product structures everywhere, and there is a notion that you can prepare states which are in a product state for your initial state for the 2 independent masses. So I think that would be the reason of why you should care, is that we are already at a regime or a period of time in which we're trying to probe regimes in which low energy quantum gravity might play a role. And the big question is like, okay, so how do we improve everything that we did so far so that we can talk meaningfully about subsystems, about things getting entangled, so on and so forth. Here just leave some food for thought, which is the fact that we learned, as we start with the talk, that space and time were not only were not absolute, but were also dynamical. And the analog of space and time, in my opinion, in the Hilbert space level, is what we call a subsystem. And so the question is, how can we maybe improve, and do we need to improve the fact that we rely on these absolute structures in Hilbert space when you think about subsystems? And if not, if we allow that to be more relational or dynamical, what can we learn with that? And with that, I finish here. Thank you.
Thank you, Guilherme. Are there any questions? Quick questions. We don't have much time. Sebastian.
So in some of the results relating the different notions of independence, you had assumptions about the dimensionality of the Hilbert space, for example, and also the boundedness of the operators. And even in quantum mechanics, that sometimes has to be extended. So what does this mean then for the different notions of independence in quantum mechanics already?
Yeah, very good. So I presented the most vanilla possible diagram, and there is extensions to pretty much everything that I discussed. And if you're curious to actually learn more about that and how that applies to more general quantum systems, even in the concept of pure quantum mechanics, there is an excellent review by Stephen Summers from I think 89. It's a thick, big review, extremely technical, but pretty much everything that you want to know that goes beyond von Neumann algebras, C-star algebras, and other more sophisticated quantum systems, that's the place I guess you could start with. Happy to also give you more papers. Yeah.
Okay, let's thank the speaker again.
Thank you.
And the next speaker